In this section, we're going to discuss complements and conditional probabilities. This is when we're going to talk about we get at least one. Those are considered conditional, the probability that an event occurring when we have additional information. So we will definitely have to maneuver some things here in this section. Be very careful with the verbiage. Normally we would also discuss Bayes' theorem, but in this course we are not going to be discussing Bayes' theorem. Okay, complements, at least one. Okay, so at least one has the same meaning as one or more. Okay, so that's what at least one means. So the complement of at least one, or the complement of one or more, means less than one, which means zero. So that means you get no occurrences. So if you're ever given at least one, the complement of that is none. So that in itself is going to be very useful. So A is going to be the probability of at least one. The complement is going to be the probability that event will be that you're getting none. So the probability of A not occurring. And again, remember, you can always do this as the probability of at least one occurring is equal to 1 minus the probability that none occur. Make sure you write that down somewhere in your notes because we're going to use that a lot in this section. So let me give you an example. Factory global manufacturing company has manufacturing products with a defect rate of 15%, which is awfully high for a defect rate, but I digress. If a customer purchases 12 of these products, what is the probability of getting at least one that is defective? Okay, so this is what we're trying to find. We're trying to find the probability that at least one is defective. Just disappear. So we need the probability that at least one will be defective. Okay, so we know that is 1 minus the probability that none are defective. That is what we know based on what we have. And we know that none are defective, right? We can find that from what we were given because it says 15%. So we need 1 minus. Okay, if we have a 15% defective rate, right, if A is the defective rate is 15%, then we know the complement of A, which is the none, will be 85%, which is very high. So we want the probability that none are defective. Now, this probability, let me erase this. We will need to find 12 of them in a row that are not defective. So we're going to use the 0.85 for the first one, and then the second one, and then the third one, and we're going to keep going, right, for 12 of them. So an easier way, rather than writing it out 12 times, the easier way to do that would just be to write 0.85 raised to the 12th power. That would be a little bit easier to put in your calculator than to multiply that 12 times. So when you put that in your calculator, you get this 0.85 to the 12th power. You get 0.142. So 1 minus that 0.142 is going to be 0.858. Okay, so what does that mean? The interpretation part is really important here. So that means that for those 12 products, there is an 85.8% probability of getting at least one of those items that is defective. And if I was the head of quality assurance at this company, I would be irate because that is way too high. If you buy 12 items, you should be relatively confident that all 12 or 15 of those items is going to be, a quality product. But to have an 85.8% chance that at least one of them, that means multiple could be defective. That's way too high. So very important that we understand what that means and those rates. Conditional probabilities are a little bit trickier sometimes. Remember, that's where you have that bar. So the probability that B bar, which means given that A has already happened. And this is gonna be a little bit tricky. So the formal approach is the one I like because I'm a big fan of formulas. The probability that B given A is equal to the probability of A and B divided by the probability that A. Okay, so you'll need to do an and then divide. And I'm going to walk you through, there's a big example about drug screening, and rather than us trying to do it, I'm just going to walk you through the entire example because it's quite complicated and there's a lot of steps to it. So I want to just walk you through it step by step. All right, so here is the initial information that we were given about this pre-employment drug screening. All right, so here are all the results. Oh, so if the subject does use drugs, there were 40, so again, we had 45 people that tested positive when they did say that they use drugs. So that is a true positive test, right? They say they use drugs and it comes up positive. But we had 5 people who said that they used drugs and the test came up negative. So that would be a false negative. Of the subjects who did say that they did not use any kind of illicit drugs, 25 of them tested positive. And those are called false positives, where it's not happening, but for some reason you test positive. And people are like, well, how could that happen? That seems ridiculous. Well, I can give you a perfect example. I can't donate blood to the Red Cross because the test that the Red Cross uses to test blood, I show up as a false positive for HIV every single time. I don't have HIV. I've been tested several times, but it comes up positive every single time. And it's just because I have allergies. So that you never know why you might be getting that false positive. And then of the subjects who didn't use drugs and tested negative was 480. So those are your true negatives. All right, so we are going to walk through this problem. Okay, so part A, they want us to find if one of the 555, so they added up all these, it adds up to 555, by the way. If one person is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. So what you want to find is the probability that you have a positive given that they do use drugs. And then they want you to, again, if you choose one of the 555 test subjects at random, find the probability that the subject actually uses drugs given that they had a true positive test. So 2 different situations, so we're going to talk about both of them. All right, so let's talk about part A first. So we want the probability that we have a positive test result given that the subject does use drugs. Okay, so we are going to take those, so we have to assume first that the subjects use drugs. So we're only going to deal with those 50 subjects that were in that first line of the chart, the 45 that were true positives and the 5 that were false negatives. So of that group, if just that group, not the whole thing, just that one group, the probability that we have a positive test result, given that they are using drugs, so we know just to use that top line, those top 50 people, 45 of them are going to test positive. And that is where they get that 9%. That should be a 90%. Decimal place is off. There you go, I fixed that decimal place. Had to fix the decimal place, it was driving me crazy. All right, but if we take the formula approach, like let's just use the formulas and go all the way. So the formula at the bottom there of the slide says that the probability of that happening is the probability of A and B divided by the probability of A. So this is, we have to use all the data. So the probability that the subject uses drugs and had a positive test result. Okay, so that was in the top upper part of that chart, 45. 45 people used drugs and they tested positive, those true positives, out of the 555 people. So that's the probability of A and B. And then you have to divide that by the probability that the subject uses drugs. Now, from that chart, we know there were 50 people who said that they used drugs. So 50 divided by 555. But notice, when you have those 2 fractions that you're dividing and they both have the same denominator, the denominators don't matter. So you still end up with 45 divided by 50, which is still that 90%. So notice whether you use the intuitive approach or you use the formal approach, you are going to get exactly the same answer, which I kind of like about probabilities because sometimes it just makes sense to go intuitively with the problem versus formally. Then you get smaller numbers and less to work with. But even if you go the formal approach, you should get the same answer. All right, now let's look at part B. So part B says we want to find the probability that the subject uses drugs given that they had a positive test result. Okay, so this time we're just going to look at the first column of the positive test results and nothing else. So we had 45 people who had true positives and 25 people who had false positives. So that gave us 70 people total. So that's where that 70 in the denominator came from. There were 70 people total that we were looking at. And of those 70 people, 45 of them were true positives, where they used drugs and given that we knew they had a positive test result. So that was 45 over 70, which gives us 64.3%. when you're manipulating those, just because you have a probability that you have a positive test result and we know that they use drugs isn't going to give you the same probability as the subject we know uses drugs given that they had a positive test result. Those two things are going to be very different. So again, wording is going to be crucial in these problems, and that's usually where students can sometimes struggle, is because the wording can be a bit tricky and you really have to think about what you're doing. All right, so very important that you know that inverses, like if you reverse them, the probability of B given A is not necessarily the same as the probability of A given B. They could be, that's possible, but it's not very likely. So make sure that you know that those two things are not the same. A lot of people will confuse those inverses, the probability of B given A versus the probability of A given B. Sometimes they think they're equal, sometimes they use them in place of each other. There's lots of things that make some mistakes that you can make with that, so just be super careful. So let me give you one more example so we can talk about the confusion of the inverse, because it can be very complicated. All right, consider these events. Okay, so the event D is that it's dark outside, and the event M is that it's midnight. Okay, so we are going to conveniently forget that in Alaska, it could be midnight and it's still going to be light outside. I used to work in Alaska, so I can tell you that's true. So we're going to kind of conveniently forget that Alaska exists here. So the probability that it's dark outside, given that it's midnight, should be 100%, right? If we know it's midnight, then it should be dark. Like, it's the middle of the night. It should be dark. So that should be 100%. But the probability that it's midnight, given that it's dark outside, well, it's dark outside at 11 o'clock, it's dark outside at 1 o'clock, it's dark outside at 2 o'clock. So that would be a 0, because the probability that it's exactly midnight, given just because it's dark, that's 0. There's tons of other times where we could go outside and it's dark. Doesn't have to be midnight. So those two are very clear that they're not the same thing. So just, again, you just have, it's just a semantics thing, and you have to just be really careful. Critical thinking is going to be key when we're talking about this verbiage. All right, so good luck on the homework, and hopefully I'll see you back for the next lesson.